In the world of electrical engineering, engineers often need to deal with how changes in electric or magnetic fields affect motion or any other aspect of an electric circuit, such as resistance, current, and voltage. In order to do so, they can use multivariable equations such as the Maxwell equations, or any other electromagnetic law such as Lenz's law or Ohm's law, which analyzes multivariable and multidimensional properties. In the last video, I explained the multivariable aspects and applications of Faraday's law, but in this video we're going to be looking at an electromagnetism problem, which applies Faraday's law and utilizes multivariable calculus. Here's the problem, which consists of 3 parts. A line of charge, lambda, is uniformly glued onto the rim of a wheel of radius b, which is then suspended horizontally. Although it is originally at rest, the wheel is free to rotate, and the spokes are made of some non-conducting material like wood. In the central region, out to a radius a, which is less than b, there is initially a uniform magnetic induction, B, pointing up. Now someone turns the field off. A. Use Lenz's law, and whatever conservation laws that might be needed, to qualitatively describe what happens to the wheel after the magnetic induction field is turned off. Does the wheel stay at rest, or is it set in some sort of mechanical motion? B. Now, quantify the answer you gave in A, again using the needed laws, either from conservation arguments and/or electromagnetic considerations. Does the final state of the wheel depend on the details of how B is turned off? C. If you determine that the wheel is set in some sort of motion by the disappearance of the magnetic induction, then specify exactly what was the source of the motion and the agent responsible for this motion. Be specific. Let's begin with part A. It asks us to use Lenz's law, alongside other conservation/physics laws, to qualitatively describe what will happen if we remove the magnetic field the wheel is currently under. If you remember from the last video, one of the Maxwell equations is Faraday's law, and it states that a change in magnetic field will induce an electric current, as evident by the partial derivative of the magnetic field being equal to the curl of the electric field. Turning off the magnetic induction causes a change in magnetic field, which, according to Faraday's law, will cause an electric field to curl around the axis of the wheel. The electric field that is induced exerts a force on the charges glued to the edge of the rim, and the wheel starts to turn. Lenz's law states that an induced current flows in a direction such that the current opposes the change that induced it. So, in accordance with Lenz's law, the current, and thus the direction in which the wheel will rotate, will be counterclockwise, so that the charge's induced magnetic field opposes the initial change. Now let's move on to part B, where we go through the math to support our answer in part A. In the last video, we talked about Faraday's law in its differential form, but for this video we'll talk about it in its integral form, which involves the contour integral of the electric field over changes in length, and the rate of change over time of the magnetic flux, described by the integral of the dot product here. Magnetic flux, by the way, is the measurement of a magnetic field in a given area. It's a different form, but it means essentially the same thing. A change in magnetic field will induce a current on a closed loop. We can begin to simplify the right side of the equation by calculating magnetic flux. This can be done using a double integral, since magnetic flux measures the magnetic field in a certain area. Using polar coordinates, we can set up an integral that takes the area of the circular region that the magnetic field is initially in, with the outer integral from 0 to 2 pi with respect to theta, and the inner integral from 0 to the smaller radius a with respect to radius r. Inside of the integral is b, the magnetic field, times r. Performing this double integral leaves us with pi a squared, the area of the circle. Now that we've calculated flux, we can replace it in the Faraday's law equation while assigning the derivative operator to the magnetic field B, since the area stays constant. Next, we're going to consider torque, which is the rotational kinematics equivalent of force, and is defined as the cross product between the torque arm and force. In this equation, r represents the radius or torque arm, and E lambda dl represents the force exerted on the charges on the rim. Next, we're going to integrate the torque over the rim. The first step in this process is to evaluate the torque cross product. We can replace r with x, which represents the radial direction. It's also important to note that while x and dl are vectors, E and lambda are not. The x vector goes along the radius of the wheel, while the dl vector goes along the circumference perpendicular to the radius, so their cross product will result in a vector pointing upward in the z direction. The magnitude of the vector of the cross product is then the product of the magnitude of vector x, which is the radius b, and the magnitude of dl, which is E lambda, which leaves us with this vector. Note that the E sub z here is meant to represent the direction of the vector. Now it's time to integrate. Since b and lambda are constants, you can take them out of the integral. We're left with the contour integral of E dl, which, as we found earlier, is equal to negative pi a squared dB dt. So we can substitute that in here. Now we are left with this equation. Angular momentum is defined as the integral of torque. So now, in order to determine what effect changing the magnetic field has on the angular velocity of the wheel, we are going to integrate the equation we found. Everything that is not the magnetic field B can be considered a constant, so we can take everything out of the integral. And the dt in the definition of angular momentum cancels with the dt and dB dt. So we are left with lambda b pi a squared times the integral from b0, the initial state of the magnetic field, to 0, the final state, with respect to the magnetic field. Taking this integral, we're left with this equation. Angular momentum is also defined as L equals I omega, where I is the moment of inertia or rotational kinematic equivalent to mass, and omega is the angular velocity. Using this equation, we can substitute L with the integral we found, and then divide by I to find the angular velocity, and this is the equation we're left with. This equation tells us that the angular velocity of the wheel does not depend on the way the B field was turned off, since it only takes into account B0, the initial magnetic field, instead of the change in magnetic field, dB dt. Part C only asks us to identify the source of the motion of the wheel and the agent responsible for the motion. According to the law of conservation of angular momentum, the system's total angular momentum cannot be different before or after the motion unless acted on by an outside torque. So, since the wheel has acquired a net quantity of angular momentum with its rotation without an outside torque, the electromagnetic fields must have lost an equal amount of momentum. Therefore, the source of the motion was the initial angular momentum present in the electromagnetic fields, and the agent for the motion of the source is the electric field induced by the cancellation of the magnetic field B. Now that we've gone through a rather math-intensive problem, we are left with one question. How would an electrical engineer actually use this information? Well, by going through the problem, we have discovered that a changing magnetic field would cause a wheel of these specifications to turn. We also found out that the way we turn off the field has no effect on the wheel's angular velocity, but the magnitude and properties of the initial magnetic field does. If we had actual numbers instead of letters, we would be able to calculate the angular velocity, flux, momentum, or any other properties we derived in this problem. An engineer can use all this information to construct some sort of device that plays off of the principles of electromagnetic induction, a spinning wheel powered only by the switching off of a magnetic field. Doing such problems allows engineers to be creative with their designs while adhering to all the proper physical and mathematical principles.